Okay, give me 1 second here. Perfect. You're good to go.
Okay, thank you. So yeah, just a quick summary again. I'm Connor. I'm from Wildfire Predictive Services team. We work with BC Wildfire to make use of data to help drive planning decisions. This talk is about an incident that happened last week with our Postgres database running out of space, and what we learned on the internals of Postgres and how we came to solve it, and some learnings from that. Yeah, let me just go to the next slide here. A background on our current project that we're working on. It's currently a prototype, and so it's not operational in the sense that people are using it, but we're demoing use cases in front of users using a live application. This application is called the Auto Spatial Advisory, or ASA for short. And basically, it ingests geospatial data that's generated from weather stations daily and highlights parts of the map that are considered hot or areas of concern day per day. So that's just a quick overview. So there's all this data that you see on the map here. It's all those pixels are stored in what are called GeoTIFF files in the GIS space. But we also process those files and store them in Postgres to allow us to use PostGIS extensions for doing more analytic features. So that's just a little bit of background of the application we're currently working on. And so because this data is sent multiple times per day, we opted for a message queue system to notify us when that data is available and where it is. So we receive these messages over the queue. Our consumers in that queue process that data when they get those messages, and they store it in the database for future analytics. So we pushed this Friday afternoon, and unfortunately, there was an unbounded queue check on our queue, which meant that messages were being received and processed, but not being acknowledged. So that means that our queue server was continuously sending out these messages, and our consumers were continuously processing this data to the point where we hit our limit in our Postgres setup, our PVC limit of 65 gigs. So we had an issue, we had some outages, and so this is sort of our debugging story. The good thing, like I said before, this app was a prototype, so no users relied on the data. We were free to delete it and just reprocess it in the future when needed. So that was one silver lining here. But as we found out, deleting data in Postgres is not trivial. So I'll walk into how that works out. To do that, just a brief history on Postgres. It was published as a paper called The Design of Postgres by Michael Stonebreaker, who I believe also spearheaded the implementation. This is their paper that was published in 1986. It's actually quite readable, and the sections are isolated pretty well. So if you're only interested in pieces of it, of the original design, it's pretty simple to pick up. Maybe not simple, but digestible. The key ideas that were listed were these 6 design goals. So as you may know, it has support for lots of complex objects. So we see things like PostGIS has like native geospatial types that you can store in the database. And there's a few other really critical design decisions here. But what we're interested here is how they designed the database management system for crash recovery. So what does that look like? The way that Postgres makes changes is that it stores each change as sort of like an event, and it's called the write-ahead log. So when a change, when an update, insert, delete is requested, that's actually written as an event in this log. So this is written first, and only after that's been flushed to disk will the actual change happen on the database. And the reason for this is that in the event of a crash, you can replay that log from start to finish and have the exact same state that has been recorded at the time of crash. So it's a way to recover from failures and have sort of a resilient crash recovery mechanism. So given that, we have this write-ahead log. We have all these changes that are logged to disk. It's stored in this pgwall directory, and you can replay this log to get to your database to the same state as it should be. And one of the interesting consequences of this design is that because it's a set of events, you can actually stream this to another machine. If you stream this to another machine, then you can basically replay that state on another machine, and you have that machine replicated. So at any point in time, you can bring up that second machine and have a nearly current copy of any database. So a follow-up consequence from that is that instead of just standbys, you can have this streaming replication set up so that you actually have live replicas at any one point in time. And this is actually what Patroni uses by default. So Patroni under the hood is streaming these logs to every one of the replicas. And then it provides on top of that a way to elect a new leader if any one database goes down. And then you can actually see this if you select from the PG replication slots table. You can see which machines are actually streaming from the leader. And this restart LSN column here, it says what logs that replica is required to start at. So it's like you're at a certain offset in that log. But what's key here is that this means that the leader cannot delete these logs until these restart LSM offsets have increased, and logs require storage. We realized we had a lot of wall logs because of the streaming replication. It was taking up a lot of space. And so deleting this, deleting any data caused some issues. The replicas in the Patroni cluster were not able to keep up with streaming laws since their PVCs were also exhausted. So we're stuck in this deadlock. We have this set of logs that need to be streamed, but the replicas that need to stream them couldn't accept them or couldn't apply them to their data sets. So we're in a bit of a conundrum. So our first solution was to scale down Patroni pods to just the leader. So there's no more replication slots. That means that the wall log space could be recouped and allocated back to the operating system. The way we achieve this is we cautiously deleted a few thousand rows at a time to avoid a large increase in delete wall logs. And then we performed a manual vacuum. Vacuum is a process in Postgres that basically goes over every deleted row and actually frees the data. So when you delete something initially in Postgres, it's still there. It's just marked as for deletion. It's dangerous though. With a full flag, it locks the table. But in our case, this table was not used. It was based on a prototype. So we went ahead with that. And that solution failed. The reason why is vacuum full also makes a copy of the table, and it copies over the live rows, which requires more disk space. So we're back where we started. Our next solution was to obviously cancel this vacuum operation. So you can actually look up operations in Postgres that are running through this SQL command here. And then you can terminate that process that's spun up, that's running that process. That's running that function. And then basically what we had to do is with this scaled down leader, we had to wait for it's got a scheduled vacuum to run. And this is run periodically. It doesn't lock tables, and it's able to free and release disk space back to the OS as it runs. So we let it run. And after a few hours, Auto Vacuum managed to clean up and return disk space to the OS from 260 gigabytes to 20 gigabytes. At that point, we were able to adjust our PVC claims back to the original size, scale up each replica again, and bootstrap them based on the wall log. So that wall log still existed, but it was able to be compacted, and it wasn't bottlenecked by replicas that were at a certain offset. At that point, our cluster was back to a healthy state. And yeah, that's kind of an overview of lessons learned from a out-of-space database in Postgres. There's a few references here if you want to check out some of the references in the slides, and also the original paper of the design of Postgres. Yeah, so that's it. I'd also like to thank Andrea Williams, who is also on the Predictive Services team. We worked together last week quite tightly. We were on a call pretty much all day debugging lists. So yeah, we learned a lot, and yeah, just wanted to share that here. So thank you.
Thank you very much for sharing your knowledge about this feature in Postgres. I didn't know that it existed, so I definitely learned something new today. And you know, from my perspective, I often get to see or get insights into some of the common problems that many teams on the platform share. And database management has been, you know, steadily remaining at the top of the list of pain points. It's something that many teams struggle with, and you know, sharing knowledge if you discover a new feature or a new workaround, like what the Wildfire Services team did today, helps alleviate some of the pain points for other teams as well. Patroni has been giving us a little bit of grief during the upgrades too. I don't know if you remember, but not the last OpenShift upgrade, but the one before that, it messed up many of the Patroni clusters on the platform, and then Kaylee Jones, our platform administrator, had to jump in and come up with a fix. And to take it to the next level, we are building what we call a canary app in our lab cluster, where we will implement some of those, you know, sensitive technologies such as Patroni, so that when we test our OpenShift upgrades in the lab cluster, we'll know if it's going to break something. So I haven't asked for you if your app did experience an outage or a service disruption as during any of the OpenShift upgrades in the last few months. Let us know what the technology is, and we will include it in the Canary app so that we can test it before the upgrade hits our production environment in Silver. Any questions for Connor and the team? And thanks again for contributing back to the community.
Thank you.
Any questions? 1, 2, 3. Thanks again, Connor. I'm going to stop the recording.
Thank you.